Have you ever pondered how time and space are connected? This question leads us to the doorstep of one of the most groundbreaking theories in the history of physics, the theory of relativity. A theory that has not only reshaped our understanding of the universe, but has also intertwined the fabric of space and time in a cosmic dance. Our journey begins with Albert Einstein, a physicist and a dreamer who dared to envision the universe in ways that were unprecedented. His monumental work on the theory of relativity is divided into two parts: special relativity and general relativity. Special relativity, introduced in 1905, is where Einstein began to redefine our understanding of space and time. It's a theory that reconciles the laws of mechanics with the laws of the electromagnetic field. It tells us that space and time are not separate entities, but are interconnected aspects of what Einstein called SpaceTime. It's like a stage where all events, motions, and transformations take place. Now imagine, if space and time are the stage, then what about the actors? This is where general relativity steps in. Published 10 years after special relativity, in 1915, general relativity is Einstein's theory of gravitation. It describes gravity not as a force, as Sir Isaac Newton did, but as a consequence of the curvature of space-time, caused by mass and energy. In this cosmic theater, the actors are the planets, stars, galaxies, and everything that has mass or energy. They dance, causing the stage to warp and curve around them, influencing the movement of others. The theory of relativity is like a cosmic puzzle, with its pieces being the entities of the universe. And the picture that comes together is a dynamic, ever-changing spectacle of cosmic proportions. It's a theory that has stood the test of time, broadened our horizons, and deepened our understanding of the universe. So, in a nutshell, the theory of relativity tells us that space and time are intertwined into a four-dimensional fabric called space-time, a cosmic puzzle that we are still trying to piece together as we continue our journey to understand the mysteries of the universe. But what exactly is this space-time we talk about? Picture this, a trampoline stretched taut. This, my friends, is a simple model of the universe. The fabric of the trampoline represents our universe's space-time. Now imagine placing a heavy bowling ball in the middle of the trampoline. What happens? The weight of the ball causes the fabric to warp, to dip, doesn't it? This is precisely how mass like stars, planets, and yes, bowling balls warps the space-time around it. But how does this relate to gravity? Let's consider a smaller ball, like a marble, rolling on the trampoline's surface. The marble, much like a planet in space, doesn't move in a straight line. Instead, it follows the curve created by the bowling ball. You see, the marble is not being pulled towards the bowling ball. It's merely following the path set by the warped space-time. This, in essence, is the magic of gravity. Now, let's add a dash of time to our space trampoline. You see, time isn't universal. It's influenced by the mass and speed of objects, much like the space-time on our trampoline. The closer an object is to a massive body, or the faster it moves, the slower time passes for it. This is known as time dilation, a crucial aspect of space-time. So, we have our trampoline, our bowling ball, and our marble, all playing their parts in this cosmic dance. The trampoline is space-time, the fabric of the universe. The bowling ball, like any massive object, warps this fabric, creating a well of space-time. The marble, like a smaller celestial body, follows this curvature, experiencing what we perceive as gravity. And time, influenced by mass and speed, adds another layer of complexity to this cosmic fabric. So when we talk about space-time, we're talking about this intricate ballet of mass, space, and time. We're talking about how objects move in the universe, how time ticks differently depending on where you are and how fast you're moving. This warping of space-time, my friends, is what we know as gravity. But how does gravity actually work in space? This question has sparked curiosity in many minds, and the answer lies in the realm of Albert Einstein's theory of relativity. Let's step away from the traditional understanding of gravity for a moment. the one Sir Isaac Newton explained centuries ago, where gravity was seen as a force pulling objects towards each other. This view, while incredibly helpful, doesn't fully capture the fascinating reality of gravity in space. Einstein, with his theory of relativity, proposed a radically different, revolutionary idea. He suggested that gravity is less about forces and more about the shape of space and time, or what we now call the fabric of spacetime. Imagine spacetime as a stretched rubber sheet. Now, if you place a heavy object on the sheet, like a bowling ball, it causes the sheet to curve around it. This is what massive objects like our sun do to the spacetime around them. They curve or warp it. Now, what if we roll a smaller object, say a marble, onto this sheet? It will move along the curve created by the heavier object. It doesn't feel a force pulling it towards the bowling ball. Instead, it's merely following the path laid out by the curve in the rubber sheet. This is how planets orbit stars and how moons orbit planets. They are following the curves in space-time created by these massive objects. This idea, this curve in space, is what we experience as gravity. It's not that the Earth is pulling us down, but rather we're following the curve in space-time that our planet creates. So, the next time you feel the pull of gravity, remember, you're not being pulled down. You're simply following your path along the curve in the fabric of space-time. Gravity, as Einstein showed us, is not a force, but a curve in space-time. You might be wondering, does relativity have any bearing on our daily lives? Well, to answer that, let's take a look at something many of us use every day: the Global Positioning System, or GPS. To pinpoint your location, GPS relies on the precise timing of signals sent by satellites orbiting Earth. But here's the catch. These satellites are moving at speeds of around 14,000 kilometers per hour and are situated over 20,000 kilometers above us. In this scenario, both aspects of Einstein's theory of relativity come into play. Special relativity, which states that time slows down for moving objects, and general relativity, which suggests that gravity, in this case the Earth's, speeds time up. So in the world of GPS satellites, their clocks, which are moving quickly, should be ticking slower than ours. But because they're so far from the gravitational pull of Earth, their clocks should also be ticking faster. It's a cosmic tug-of-war of sorts, where the net effect is that each GPS satellite's clock runs faster than a similar clock on Earth by about 38 microseconds per day. Now, you might think, what's the big deal with the difference of mere microseconds? But consider this. Light travels at an astonishing speed of nearly 300,000 kilometers per second. So, a discrepancy of even a microsecond means that light, and hence the GPS signal, can travel an extra 300 meters. Hence, if we didn't account for relativity, our GPS systems would be off by several kilometers. This is just one example of how relativity impacts our daily lives. It's also crucial in understanding the universe, from the behavior of black holes to the expansion of the cosmos. So, while the theory of relativity might seem distant and abstract, its effects are closer to home than you might think. Indeed, without Einstein's groundbreaking work, we might still be getting lost on our way to the grocery store. So, what does the theory of relativity tell us about our place in the cosmos? It's a question that invites us to delve deep into the philosophical implications of this groundbreaking theory. The theory of relativity, formulated by Albert Einstein in the early 20th century, is not just a scientific principle. It's a philosophical revelation that underscores our understanding of the universe and our place within it. The theory, in its elegance, suggests that the universe is not a static entity, but a dynamic, interconnected system. Space, time, and matter are not isolated concepts, but are deeply interwoven, continuously interacting and shaping each other. This paints a picture of the cosmos that is fluid, ever-evolving, and interconnected. Space and time, two seemingly separate entities, are merged into a four-dimensional fabric known as spacetime. Matter, in turn, influences this fabric, causing it to curve, warp, and ripple. This interplay between matter and spacetime is what we perceive as gravity. We are not merely passive observers in this cosmic dance, but active participants. Our actions, our very existence, contribute to the dynamic nature of the universe. Each of us, in our own way, plays a part in shaping the cosmic fabric. This realization brings with it a sense of unity, of being intrinsically tied to the cosmos and to each other. In essence, the theory of relativity teaches us that everything in the universe is relative and interconnected. It tells us that our view of the universe is not absolute, but dependent on our perspective and the context in which we observe it. It shows us that our place in the cosmos is not fixed, but fluid and ever-changing. The theory of relativity, therefore, offers us a humbling and awe-inspiring perspective of our place in the cosmos. It invites us to view the universe not as a collection of separate entities, but as a unified whole where everything is interconnected and in a constant state of flux. It reminds us that we are not separate from the cosmos, but an integral part of it. This, in essence, is the cosmic perspective.